All right, so yesterday we did a problem where we found the plane was x minus z plus 2 equals 0. And using the parametric equations, we were able to find the distance from point -1, 1, 2, the minimum distance to the plane, using parametric equations and orthogonality. We can do the same thing using the distance between a plane and a point. There's a formula for it, using projections, and it was one of the videos. But I thought showing how to get it two ways might be pretty good. Go ahead and work on this a couple minutes and we'll do it together. So this comes from doing a projection. We got some point P off the plane. We don't know the point on the plane that's the shortest distance, but if we just pick any point on the plane, we can make a vector between that point on the plane and our target point. and project that onto the normal vector, and that would give us the distance. And so this formula comes from that. If you watch the video, I walk through it's doing it a little more. That's where the video comes from, but our A, B, C, D comes from is the equation of our plane. So we have AX plus BY plus CZ plus D is just that X minus Z plus 2. And N is our ABC. And that comes from the same thing. We take the coefficients of our variables on our plane. N equals 1, 0, -1. So when we're setting up our distance formula using this, I have X comes from this, our point. So that's -1. We've got no Y, and then I've got minus Z, which is -2. And then I've got +2. That's my D. And on the bottom, we have square root of 1 squared plus 0 squared plus -1 squared. Clean up the top, we got the absolute value of -1. The bottom is the square root of 2. And so we get 1 over √2 or √2 over 2 units. So there's more than one way to find that distance. And that formula, it does come from doing the magnitude of the projection. So if you like learn what's or understand what's going on, you don't need to memorize the formula. You could just do it if you know the projection formula. Projections onto N with QP would be QP dot N over the magnitude of N squared times N. And then when we do the distance, we're taking the magnitude of this. The only part that's still a vector here is that part. Because QP dot N is a scalar. And so this cleans up to QP dot N over the magnitude of N. And so you can see the magnitude of N is our A squared plus B squared plus C squared. QP dot N is ABC. That's the N, and we're dotting it with X minus X naught, Y minus Y naught, Z minus Z naught for the QP, where the Q is our X naught, Y naught, Z naught. And the D ends up coming from distributing this ABC to this negative X naught, Y naught, Z naught, combining all the like terms because they're all constants. And that's the derivation. We did it, and I did it in the video. So if you want to see it again, check it out there, or memorize the formula, or use the parametric equations, which we did yesterday. You guys ready for another concept?
Yes, sir.
Yes, sir. I like. Let's see. Where am I going to pull it from? I think you'll find it. Do it there. Share. Let's grab number 20 here. We're gonna do number 20. So I will put this up. Shit. That looks lame. I'll have to fix it later. So I'm going to write down the equations on the paper so we can work with it. I've got x plus 2y minus 2z equals 5, and 6x minus 3y plus 2z equals 8. And these are two planes. I've got the equations written down. I'll bring this back up. These are two planes that intersect. I should make that a dotted line. They intersect in a line, and we're looking for the angle right there between the two planes. So it just so happens that if we use the normal vectors for the planes, and I don't think my picture is going to do it justice, this angle here matches this angle here. So
I have a question.
Yeah.
Do you know any softwares where we can like graph? Because I can do planes on GeoGebra, but I can't do like just pure vectors. Is that possible?
I can look into it.
Okay.
A vector, so you can't do a line on GeoGebra?
I definitely haven't been able to either.
I don't.
Oh,
unless
wow,
I'm
that's
just
lame.
I don't know if I'm doing it wrong or like what exactly, but it doesn't seem to work.
The 3D graphing I guess there's not really much demand for 3D soft modeling, or not 3D modeling, but 3D graphing.
Yeah. I can do the plane, but when I'm trying to like visualize what the lines are doing, it doesn't work.
Huh. I'll look into it later. See if I don't use GeoGebra, but there's got to be a way to. There's no way they made a fucking math software without the ability to do one of the most basic functions in math. I can't believe they would have no ability to make a line. So I'll check it out. I'll look into it while you guys are practicing. Okay, so let's get back to this. We've got these planes. We're trying to find theta. The normal vectors make the angle. So how could I get this angle using what I know of vectors?
Angle between the normals. I'm hearing angle between the normals.
Yeah, how do I find it?
Maybe like use that equation.
Which equation?
Cosine theta equals
It comes from the dot product.
The dot product over the magnitude.
They're saying using dot product to this?
Yeah, so dot product will work. Two forms of the dot product. We've got magnitude of n1, magnitude of n2, cosine theta. And since we're looking for theta, we're just going to, divide by the magnitudes. So we got cosine theta equals n1 dot n2 over magnitude of n1, magnitude of n2. Fuck, there's not enough lines there. So what's n1 and n2? Seems like we need that, don't we?
Got 1, 2, and -2.
1, 2, and -2 is one of them.
6, -3, and 2.
6, -3, and 2 is the other. Where did you get those from?
From the parametric equations, the coefficients.
You got them from the coefficients on the planar equation. Yeah. All right. Well, let's do it. What's N1 dotted N2? We've got 1, 2, -2 dotted with 6, -3, 2. All over magnitude of N1 is 1 squared plus 2 squared plus -2 squared. And then we've got magnitude of N2 is 6 squared plus -3 squared plus 2 squared. And that's my cosine theta. So what do we get on top? I got 1 times 6 is 6. 2 times -3 is -6. And -2 times 2 is -4. On bottom, I've got 4, 4, and 1 is the square root of 9. Yes, I know that simplifies. I put a 3 there. That's not true. 6 squared. I got 36 plus 9 plus 4 is the square root of 49. Look at that. Nice and easy peasy. That's my cosine theta.
Yep.
And it wants it in degrees. And the question said the acute angle. So I know cosine negative is in the second quadrant. I got an angle that's bigger than the acute. But we can find it real quick. Let me shift modes here. So I'm going to do cosine inverse -4 divided by 21. So this cosine inverse of that gives me 100.98 degrees. That is not an acute angle. So that must be this angle right here. The way I did the picture. But I know the full going from one side of a plane to the other is 180 degrees. So I know this plus the theta I'm looking for is 180 degrees. So theta will be 180 minus that. Which is what, 79.2?
Yeah, 79.02.
02, my bad. 02. Let's see. I know I have a problem like this on the test. Do I ask for the acute angle?
If I put on screen, put on screen, we can find it for you.
I did ask for the acute angle.
Can you believe it, Mr. Jones? One of the students suggested that to put it on the screen for them to so they can help you find it.
I think your dot product should have an absolute value sign around it. We just looked at in the book, and it should have an absolute value, so that gets rid of that -4. Just be 4.
Yeah. No, I
Yeah.
don't think so.
Yeah, just show me.
So if you take out the,
So that's.
you get 79.02, and this is the positive.
But I think that's more of a, so we're initial.
What page is it
Hey.
on?
Page 720.
720.
That's a,
She gonna change the question to finding the optimal angle. For real. Make sure you got the angle.
acute angle. Well, that work.
Why
I
don't,
feel
why
like
don't
that's-
you, why don't you do the calculation? Why don't you do cosine inverse of 4/21? Do the absolute
That-
value and tell me what you get.
That,
Tell me if you
that
get a
would-
different answer than what I get.
that will actually give you the same answer because I realized it was the obtuse angle, so I removed the negative and it gave me the 79.02 degrees.
Right. So
So-
79.02 is
usually
also
that's
cosine
situational.
inverse of 4/21. That is 79.202.
Yeah. But I also think that's kind of situational, and you can just as easily mix up your equations and accidentally put that in when you don't want it in there and screw yourself.
Yeah,
up.
that absolute value is not always present. They're only putting it in there to find the acute angle. And I don't need to do that if I understand that angles in a plane add up to 180 degrees. I don't want to put that in there because it's not always true. That absolute value is not always true.
Yeah.
Because the other angle it's generating is this angle right here.
Right.
I mean, the angle I had, that 100.98 is the big angle. So I don't know that you want it. I mean, you can, but this is very particular. This is only for acute angles. Do you really want to memorize a specific version of cosine theta for acute angles using the dot product, or you just want to know that angles add up to 180 when it's a straight line? You should already know that from trigonometry. So that's old news. If you want to memorize it and use it like this, go right ahead. It's up to you how much you want to spend memorizing. I think you're generating more work for yourself.
Just try not to mix it up with the actual equation.
This is the actual equation. That's the real for all
Yeah,
cosine
I know.
theta. Yeah.
I'm
Uh,
saying don't mix it up. Don't mix the accidentally put in the opposite values when they're really not. They really shouldn't be there.
Right. So yeah, definitely. Because cosine theta should go up to 180 degrees. All right, so beyond the whole, is there the absolute value or not? Is there any other questions for this type of work?
Could you take a look at maybe 27? It's kind of confusing to understand what was going on.
I was gonna do line of intersection with the problem we're doing.
Oh, okay.
So, but yeah, let's do line of intersection. I didn't want to do 27 because it gives information already. And like, I want to show how to get a point on the line of intersection in case they don't give you the point. That's baby steps. So let's do these same equations, these same planes.
Professor Jones, could you actually get the same answer if you use sine? Because when you use sine, you have to do cross product, though, right? So
Yeah,
that
you
would
gotta
probably-
use the cross product. I think the cross product is more work. But if you're already looking for the line of intersection, you will have done the cross product anyway, so you could. In this
Should give
problem,
you
they
the
just
same
ask for the angle, and the dot product is quicker.
True.
Because you still need, for the cross product one, you still need the magnitude of the n and the magnitude of n1 and n2. The only difference here is dot product is much quicker than cross product. But good question. It's a good question. Yes, we can. So we still have our same n1 and n2 in our picture. that line of intersection right there, that angle is from here. And it's orthogonal to N1 and N2. So the line of intersection is orthogonal to both. So we can find that the vector for the line of intersection using cross product. So that's what we'll do. So N1 and N2 cross product. N1 and N2 are orthogonal to the line of intersection. So we already said what our N1 and N2 were. They changed it. No, they're still the right values. Let's set up our matrix.
So with that statement right there, is there like a good way to visualize what that means? Like, I don't know if I'm the only one having a hard time like imagining what N1 and N2 being orthogonal to the line of intersection means. Like,
So they're wondering how,
is it orthogonal to the two planes? Is it orthogonal just in that line intersection, like that, just that specific exact line point?
you know, the two planes, how they intersect?
Okay,
Yeah.
here's a perfect example.
Oh, I was gonna just explain it.
Okay, let's hear what you got.
So,
Floor is yours. Let's see what you got.
so you know how the planes intersect?
Yeah.
The orthogonal, you have the N1 pulling out and the N2 pulling out, right? What they're both orthogonal to is the line between the two planes that are intersecting.
That's true. Lawrence, let me give you an example you can easily visualize. Check this out, Lawrence. You're gonna like this. Z, Y, X. If I have the XY plane, it's like this. And Z is the normal for it. If I have the XZ plane, so that's N1. If I do the XZ plane like this, the normal for that is Y. It's sticking straight out of it. That's N2.
Right.
What's orthogonal to both the Z axis and the Y axis?
The x-axis.
The X axis. So that's a better way to visualize it with planes that you know. The same things, and we have that line of intersection of the XZ plane and the XY plane is right there. That's our line of intersection, and it is the X axis, and it's orthogonal to both.
Okay.
It's kind of weird because you're picturing two planes, then you're picturing an arrow sticking out of each plane, and you're making the arrows touch at their base, and then you're finding the vector from it. It's a little hard to visualize. I think that the whole XYZ axis is a good representation for it, easier way to view it. Does that make sense?
Yeah, that makes a little more sense. It's just like, it's hard. Yeah, I don't know. It's hard to visualize without that kind of situation. But
Yeah,
I just get used to it over time.
I was struggling too, like Lawrence. Now, like looking at this, it's easier to understand.
Good. All right, so what do we got here? For I, I've got 4 minus 6. For J, I've got 2 plus 12. And for K, I've got -3 minus 12. So -2, 14, -15. That's like my N3. Let's just call it B. Okay.
It should be a negative.
Oh, yeah, that should be -14
You're right.
in
The
the
negative
J's.
outside. I see it. I missed the sign right here. All right, so we've got our vector B, -2, -14, -15. And now we can write this line as L equals a P naught plus TB, and we have our B. We just need to find a P naught. We need to find a value that exists on that line of intersection. So we're going to have to use both equations. Easy way to do it is to set one of the values to 0 and get it down to, like, we will definitely have x equals 0 somewhere on both lines. So let's do that. What I'm doing is to pick which value I want to do to 0. I'm looking if I zero out x's, what do I have? I've got two equations, 2y minus 2z equals 5 and -3y plus 2z equals 8. That looks like two equations I could work together with pretty quickly. Do I want to zero out y? Y would work just as well. This 2z and this -2z are going to make it easy to figure out two equations, two unknowns. If I get rid of z, I got a little more work. I don't have any matching coefficients. So I'm going to use x, but we could use y just as easily.
Could you hold on
so
for a second?
Yeah, I was gonna say, did you say that so that cross product right there, is that parallel to the line of intersection that we're trying to like find, or?
Yes. It's
Okay.
parallel to the line of intersection, and we're trying to find the actual line of intersection by picking a point on it.
Right, okay. And it doesn't matter which parametric equation you use. Like when you're plugging in your x equals, you're just trying to find the most convenient one, right?
Right. If I did like in the video, I did z equals 0 when I was doing this because the z problem was easier. What I'm doing is looking at, I'm going to have two equations, two unknowns if I zero one of these out. And so I'm just looking which one's the easiest. When I see that, I see 2y minus 2z equals 5, 3y plus 2z equals 8. If I add these together, the z's go away. And 2y minus 3y just gives me a -y. This looks like this might be a pretty easy system of equations to solve. So that's what I'm going to do. If I do x equals 0, I'm left with 2y minus 2z equals 5. -3y plus 2z equals 8. So if I add the equations, I've got -y equals 13. So y equals -13. And now I just got to go back and plug it into one of these. 2y minus 2z equals 5. I'll plug in the -13. So this is -26. I'll add 26 to both sides. I get -2z equals 31. So I'm getting z equals -31 over 2.
Could you bring the paper down?
Can I what?
The paper, you were starting to cut off.
Okay.
So like
So I've got-
alternatively, you could have just taken one of the parametric equations, right, and just worked with that and set different values to different, like, you don't have to work with
No.
both.
You got to work with both, because if you don't only work with one of them, you're only guaranteeing to find a point on that one plane. We need a point that exists on both planes. So if I just work with x plus 2y minus 2z, let me bring this picture back up. I might have a point over here and not on the line.
Okay.
Does that make sense? So I
Yeah.
need to pick one that's on both planes, and the only ones that are on both, which would require both equations. That's an excellent question. If it were that simple, I would have just zeroed out two of them and would have said X and Y equals 0 and solved.
Right.
But that's a great question. So my point that I can use one of them, there's more than one on this line, but the one I came up with here is putting it in the L format. 0, -13, -31 over 2 plus t times -2, -14, -15. If you did the y or zeroed out z, you're going to get a different value. We can look at that if you'd like.
I think
But
I
the
understand that
lines
you-
should
on the plane.
say that again, Lawrence.
I said, I think I understand that you're just getting something on the one plane and not on both of them. And that's what we're looking
No,
for.
I'm getting something on both planes. This point is 0,
yeah.
-13, and -31 over 2 is on both planes. It's on the line. If I
Right.
pick a different variable to zero out, like
Yeah.
here I did x equals 0, another point. If I pick
It'd be
another
like-
point, it's going to be a different point, y equals 0. So I'll have different things here. This would remain the same. But a multiple of t, whatever, I could plug in a multiple of t and get the other point.
So that's the whole equation for the line. You don't, because of that. Okay.
And if I had zeroed out z, I'd have even a third point. That's easy to get. And you don't even need to zero out. I could have selected x equals 1. I think that's more work. I like working with 0 whenever possible because of its destructive power in multiplication and its ease in addition.
Until you find yourself dividing by 0 or finding the natural log of 0.
Well, if you did that here, you did something wrong.
So. Oh.
Did you have a question or?
Yeah, no, I just misread it when it says L equals blah, blah, blah. I thought that was a T. And then the other, so I didn't realize it was continuing on the next part.
Oh,
Okay,
yeah, yeah.
well,
This is, maybe I'll
I thought
rewrite
it
it.
happened the other, yeah.
There, that might be a little clearer. My bad. It's a handy thing to know how to do. How often does it come up? Depends on what you're doing. Finding the distance between a point and a plane seems like something that comes up a lot more often or would come up more often than finding the intersection of two planes. So this is more of a line along the lines of to give you a taste of it. It's worth knowing how to do.
Out of this chapter, what do you think is like the most applicable section, like going forward? Like, what are we going to be using the most out of this chapter, like into the next chapters, you think?
The most stuff you'll be using out of this chapter is related to the parametric equations, and we do the dot product, cross product especially. Dot product comes up, but cross product when we're doing a curve, because we've been doing lines here, L, but eventually we have a curve. I think I showed you guys this the other day. And this is a three-dimensional curve, not just in XY, but in 3 dimensions. At any given point, we can find the tangent line.
I know we can
And I can find a line that is normal to it. And the vector that right now is coming into or out of the page is called the binormal vector, which we would get with the cross product.
TNB, I remember that.
PNB, well, yeah, it's a fun section. It's a pain in the ass. Wait for it.
And can turn really messy sometimes if you have very inconvenient equations.
All right.
That is for another day.
What will I do now? Let's see. Let's go into files. And I need to get this out of the way so I can see it. And practice exam here. Publish it. I will make an announcement for it real quick, so that you guys can find it easier. And I'll tell you now, and I'm going to make note here, there is an extra,
Feeling good.
there is an extra credit problem on the exam that is not listed on the practice.
It'll probably be like a tough concept question. Right? Or-
I guess you'll find out.
That's fine.
I'm telling you. I'm not telling you what it's about because I want you to study more than just this exam. Everybody's been asking, not everybody, a lot of people have been asking for the practice exam. I know why. You guys are wanting to be lazy. You want to just study what's the bare minimum. We're not doing that.
And
So
what's a few applications for this stuff that we went over today, like in the real world? Is there
Like one review project. Or we project.
let me think about it.
okay?
So we minus the speed projection. Project on that, do two pixels. Okay.
Well,
Make it normal.
when you're doing 3D graphing in the software, your software is doing that when you're looking for a point on the line of intersection in two planes. Like if you're building something and you make a corner, you're drawing something that has a corner in it. And the computer, when you're going to look for this line, it's using this information to find that. Stuff like that. A lot of the stuff you're learning in Calculus 3, let's be honest, in the real world, if you're using this stuff in real life, you're using computer software to do it. You need to understand what's going on with it, though.
Just it's like A to A.
That's cool though.
A to A.
That way, when you see something that, if you enter something wrong and you don't know what's going on with the math behind it, you may not recognize something's off with the result. But you do get an intuition with the stuff over time.
Real quick, I'm looking at the study guide right now, or the practice exam. It's like not really a big deal, but on number 5, you have like 3 points, and like 2 of them are labeled as A. It doesn't make a difference in like the actual like. So
Yeah, just call this one B.
Yeah, no, exactly. I was just letting you know if that may change later or next class.
Yeah, I'll edit it, upload a better one right now.
Thanks for the practice exam, Professor Jones.
Huh?
I said thank you for the practice exam.
Okay, so
Oh, I heard you. I said, You're welcome.
Oh.
angles between them. Angle of intersection.
We will go over this exam tomorrow. I'll try to get as much in as I can during the hour we have. But then, I will, again, if you want, I'm sure Saturday and Sunday are gonna be a walk guaranteed for Starbucks. If anyone wants to meet me on
You know how
Monday,
to eat. Yeah.
let me know.
A little better.
Yeah, I'd like to
only
on
two of those
Monday.
I didn't know two days.
You'll be doing Monday too? Okay.
Yeah.
So I'll put up on,
Now like 3.
make an announcement about Starbucks. I think I can make it do a little bit longer, these days. And give you a little bit more time than 2 hours each day. I'll make an announcement about it, though, for it being all 3 days.
Sounds good.
I'll also be doing a Zoom SI from 12 to 2 on Monday as well. For anybody who has any last questions.
One more time.
I'll be doing the SI 12 to 2 on Monday.
You'll notice between 5 and 6, 5 is find the equation of a plane. Number 6 says use the plane from the previous problem. Yesterday we showed how to do it with parametric equations. Today we did the distance formula. There is a problem like this on the exam. I don't care which method you use. If you want to impress the shit out of me, do both if you got both at time at the end.
Hey, also, Professor Jones, you said that you're gonna have the classroom open an hour early, so we can have some time to work on it, or no?
Yep, I'll be there at 7 a.m. on Tuesday morning.
Awesome, okay.
You'll be earlier than me, that's for sure.
I'm just gonna skip that. I see like grab. Blah, 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 like- No, I'm wondering what the expedited might be. Trying to think. That's what I was thinking. They're gonna clutch that. He does like business model. He's like a business analyst. He does like. It's like finding the word, my question box. He expects like some like orthogonal this, orthogonal that, cross product this type of thing. So we're just like.
What is your? What is your?
I still can't hear you.
I'll get the Zoom set up when I get there. All right.
I'll figure it out. I'm kind of doing it. Setting up the Zoom meeting myself. Setting it up.
I'll see you guys tomorrow.
Yeah, have a good day, Professor Jones.
You too.
Thank you, sir.
I don't have anything last thing, so I'll see you tomorrow.
Okay. Does anyone on Zoom have any questions before I wrap this shindig up?
No, I think I'm good. Thanks.
You good? Okay.